The focus of this GM Service Know-How release is the issue of shudder and juggle as it relates to transmission and transaxle diagnosis and service. Transmission diagnosis can be challenging enough on its own, but when other parts of the powertrain, as well as the chassis, must be considered, the challenge is further magnified. The unfortunate part is that many times the torque converter is replaced in an attempt to isolate and repair the concern. Most times it doesn't fix it. And furthermore, replacing a torque converter is not one of the easiest things to do. This GM Service Know-How release is designed to help make the transmission technician a stronger partner with drivability and chassis technicians. The objective is to look at the root causes of shudder and the other conditions that can be confused with shudder. Here's how this topic is going to be approached. We're going to review torque converter and converter clutch basics. We'll also look at TCC calibration and how it works into the equation. We'll examine how to determine the general source of shudder and juggle. You'll see how engine surge and juggle can manifest itself as a transmission concern. We'll also review common engine malfunctions that can cause surge and juggle. We'll take a look at isolating sources of shudder in the transmission. And finally, there's a review of the tools of the trade. Shudder and juggle concerns are often wrongly attributed to the torque converter clutch. This is often due to the fact that the torque converter cannot be disassembled for inspection. Most torque converters operate today without the shudder concerns observed in the past. The converter has 5 main parts: the converter pump and cover, the turbine, the stator and stator one-way clutch, the pressure plate and its bonded TCC friction plate, and the damper assembly. Here's a review of each and how they work together.
The converter pump and the cover are welded together to form one unit. Located inside this unit is the turbine, which transfers engine power into the transmission. The converter cover and pump are always rotating at engine speed, since the cover is bolted to the engine flex plate. During rotation, the fluid inside the converter is discharged by the pump into the blades of the turbine. This fluid coupling transfers power while providing vibration damping between the engine and transmission. In addition, the turbine can be held stationary by the vehicle brakes while the converter cover and pump rotate at engine speed. Located between the pump and the turbine is the stator. The stator provides torque multiplication during acceleration and vehicle launch. This increase in torque is necessary for the engine to overcome the resistance to vehicle movement. The stator is mounted on a one-way or roller clutch. The inner race of the clutch is grounded to the case through the drive sprocket support on transaxles or the pump stator shaft on transmissions. When the converter pump is rotating faster than the turbine, the rollers of the stator clutch wedge between the two races. This holds the stator stationary and provides the torque multiplication. As the fluid causes the turbine speed to approach pump speed, the clutch rollers will unwedge and allow the stator to rotate freely. When this occurs, torque multiplication is no longer provided. If the stator cannot be held stationary, the vehicle may have poor acceleration from a stop and at low vehicle speeds. If the stator cannot rotate freely when the turbine and pump are near the same speed, the vehicle may have poor performance at higher vehicle speeds. Both conditions can also result in overheated fluid, since both can generate excessive heat. Although both the pump and turbine are rotating at nearly the same speed, there is some slip. This loss of engine power directly relates to fuel economy, and that's why torque converters have a torque converter clutch. The clutch provides a direct mechanical link between the engine and transmission. When fully applied, it provides a mechanical path around the fluid coupling and reduces the power loss. However, the power loss is not completely eliminated when the TCC is in controlled slip mode. The TCC assembly is splined to the turbine. When fluid pressure is applied, it mechanically connects the turbine to the converter cover through the friction material. The TCC is normally applied in third and fourth gears. However, some applications will apply it earlier for certain failure modes, including high fluid temperature.
Torque converter clutch operation has changed a lot since they were first installed in transmissions. The first generations of TCC used a simple on-off solenoid to control apply and release. As you might remember, you could definitely feel the TCC apply as the clutch immediately reduced the slip in the fluid coupling. Well, since then, it has changed drastically. Now, the TCC in most transmissions is controlled by a pulse width modulated or PWM solenoid. This solenoid allows the clutch to be gradually applied and released, providing almost unnoticeable TCC operation. TCC pressure plates are also designed with a damper assembly. This further softens the TCC apply and absorbs some of the irregular torque pulses from the engine and the road surface. Today, shudder caused by torque converter operation has been virtually eliminated through the use of PWM control, improved friction material, and the design of the pressure plate damper assembly. Since the 1996 model year, GM has operated the TCC using a control strategy known as EC3, or electronically controlled capacity clutch. This strategy controls the amount of pressure applied to the pressure plate to maintain a slight amount of slip at all times on all units. The slip rate is approximately 20 RPM. This slip reduces the torsional disturbances between the engine and the vehicle. It's important to note that a misfiring engine can still cause a shudder or juggle that even the EC3 system cannot compensate for. This can result in a customer concern related to the transmission, even though the transmission is not at fault. Engineering also has the ability to address emerging field concerns through the modification of the TCC calibrations. These changes can be made in the field through PCM reprogramming. Many times, the field drives the calibration changes through TAC cases. Let's now review how the TCC is controlled.
During TCC apply, fluid pressure is applied to the rear of the pressure plate, and any fluid in front of the plate is allowed to exhaust. When the clutch is off, fluid is directed to the front of the pressure plate. This pushes the plate away from the converter cover. Basically, the direction of fluid flow through the torque converter controls whether the clutch is applied or released. The direction of fluid flow is controlled by TCC valves and the operation of the TCC solenoid. The solenoid also controls the amount of fluid that is directed to the pressure plate, which controls the apply and release pressure. The pressure directly relates to the apply-release speed as well as the feel. TCC operation is controlled in 6 stages. Refer to your reference booklet for complete details.
In order for the PCM to control the operation of the transmission, it must have 2 basic things: sensor inputs and calibrations. The sensors provide the PCM with information on the operating conditions of the vehicle, as well as the desired operation from the vehicle operator. Calibrations provide the PCM with programming on how to react to these inputs. Calibrations can be changed by PCM reprogramming in the field. This allows GM to address emerging concerns that were unforeseen when the vehicle was first manufactured. Calibrations and to some extent sensors are specific to the vehicle application. Many times the same type of transmission with the same torque converter will operate completely different in the various vehicle platforms. This is due to calibrations. They're customized for the operating characteristics of the vehicle, including mounting and vehicle architecture, vehicle weight, payload demands, and how GM perceives customer expectations for transmission operation.
In general, TCC decisions require the following inputs, depending on the application. There can be many more. There's the transmission fluid temperature, or TFT sensor, found inside the transmission. The engine speed input is typically generated from the crankshaft position, or CKP sensor, or from the ignition module. Some transmissions, such as the 4T65E shown here, use an input speed sensor. All automatic transmissions and transaxles use an output speed sensor called the vehicle speed sensor, or VSS. The throttle position, or TP sensor, is found on the engine's throttle body and replaces the old throttle valve cable found on previous non-electronic automatic transmissions. The accelerator pedal position, APP sensor, can be included as an input when equipped.
Now let's take a look at how TCC operation varies for 4 different vehicle categories. I'd like to welcome Dave Sprague, a powertrain calibration engineer, to give us a better understanding. Dave, welcome.
Thank you.
Let's look at a small passenger car first. What are the major elements of TCC calibration for a small car?
Well, in a small car, the calibration in the PCM controls the applies and releases of the torque converter clutch. What that does is it sends a signal to the PWM solenoid in the transmission, which controls the apply and release of the clutch.
Well, now, when should TCC apply and release occur?
Well, the TCC apply and release should occur in 3rd and 4th gear in a small car. And we will target a 20 RPM slip. And usually the apply times can be between 1 and 3 seconds, approximately.
How about vehicle speed and throttle angle? What kind of effect do those have?
Well, the higher the vehicle speed and the higher the throttle angle, we will push out our apply and release lines to compensate.
Well, now let's look at trucks. What are the elements of the TCC operation on a small pickup truck?
Basically, it functions the same as in a luxury car or in a small car. However, the slip may vary. You may see RPM slips up to, say, 40 RPM. And as soon as you get to a high enough speed, the torque converter may fully apply, and you may see 0 RPM slip.
Well, now, how about TCC apply and release? Will they be the same on a truck?
Pretty close. You may get a little more feel in a truck. It's a heavier duty application, so they may be a little more aggressive on their applies and releases.
Well, now, how does the TCC calibration change when we move up to a larger pickup truck or, say, a sport utility?
Well, on a larger pickup, say with a 4L80E transmission, we would run TCC, a full apply, 0 slip converter clutch. This allows no slip when you're driving down the road.
How about apply and release? Any changes there?
It would be similar to a truck. It's a heavier duty application, so again, you're going to want a little more aggressive apply and release pattern.
How about timing? Should the apply and release take longer since it's a larger truck?
I would probably say around a second. It should be fairly smooth. You'll see an RPM drop on the tachometer, but it should be relatively quick.
Well, thank you, Dave Sprague, for taking the time to be with us. I'm sure our technician audience appreciates being able to learn about calibrations firsthand.
My pleasure.
Thanks. Now let's look at trans-shudder, what it is and what it is not. The key to any good diagnostic strategy is having the most information possible and doing the easiest things first. Then it's just a matter of dividing and conquering. Shudder or juggle can originate from the engine, transmission, or driveline. Here's some of the preliminary information required for an effective diagnosis. First of all, what does the condition feel like? Does it feel like driving over freeway rumble strips? Does it feel like the engine power pulses up and down, sort of a low-frequency fore-aft motion of the vehicle when the throttle is held stable? When does it occur, and how does it change? During a vehicle launch, during a shift, during a steady-state gear, during TCC apply or release, during 4th gear with TCC applied, at highway speeds, at constant throttle. And here are 2 final questions. Does it only happen intermittently? Does it occur only on specific road surfaces? Some of these questions can be answered from the repair order. Others will be answered through investigative testing. However, we realize there are some simple rules of thumb that can be applied to shudder and juggle concerns. But above all, do not throw out any possibilities until thorough testing has been performed. The rules of thumb are as follows. First of all, shudder feels like driving over rumble strips on the freeway. Shudder is generally associated with either the transmission or the driveline. Driveline shudder generally occurs during acceleration and is more pronounced during the vehicle launch, usually referred to as launch shudder. However, some driveline shudder can be noticed at a specific vehicle speed range, such as a wheel imbalance. Transmission shudder generally occurs during gear shifts or when the TCC is being applied or released. The sensation of engine juggle is slightly different than trans shudder. Juggle, defined as a bucking or jerking motion, feels like the engine loses power briefly and then regains it. It's generally an engine concern. It can be isolated when the engine is under a load at a stable throttle angle and the transmission is in a steady state gear, although it can change during a shift. It can be more pronounced when the TCC is applied, since the engine is mechanically connected to the transmission and driveline. At this point, the fluid coupling cannot damp the vibration from the engine, and the juggle can be confused with shudder. Let's now build upon these characteristics and see how they apply to vehicle diagnostics.
The first step is to check for transmission and engine DTCs. Always repair the DTCs first. Even if it doesn't appear to be the problem, repair it. Many of the sensors used for engine control also affect the operation of the transmission. Also, take a look at the misfire counters. The PCM can be detecting misfires, but they may not be to the point where a DTC is stored. If the misfire counters are increasing or high, consider the possibility that a misfire is causing the shudder or juggle. Make note of this and continue with the testing. While performing preliminary checks, take the time to search for bulletins and PIs. These often contain known concerns and an effective repair. Also, GM may be aware of a shudder or juggle concern with the vehicle and has a calibration to repair it. Next, take a look at the engine oil and transmission fluid. These can provide a wealth of information. When checking the engine oil, note the condition and level. Low level can indicate mechanical concerns, which can result in juggle or shudder. The same holds true when the engine oil is dirty, contains debris, or is contaminated. Check transmission fluid level and condition. A low level can be an indication of a leak and can result in slipping friction components, shift clutches, and the TCC, as well as overheating. Also, don't forget to make sure the fluid is Dexron 3, the only fluid to be used in GM transmissions. If the fluid is red, it's in good condition. Some small metallic particles will be normal, but large chunks indicate a real concern. Hard parts are damaged. If the fluid is brownish red, this is also normal. As more miles are put on a transmission, the friction plates as well as the fluid will begin to wear. This will discolor the fluid. Also, over time, the fluid and friction materials will begin to lose friction properties. This is why transmission fluid must be changed following the routine maintenance schedule for the specific vehicle. This is also true for the TCC. If the fluid is degraded, the transmission will be more prone to shudder. If the fluid is dark brown or even black and has a burnt odor, the fluid has been overheated. Also, burnt fluid can be an indication of damage to the friction plates, seals, and washers. Generally, when this type of fluid is found, there will be a transmission concern. Burnt ATF will affect other internal components.
Changing dark brown burnt fluid can cause the already damaged clutch packs to show up in a road test as poor shift feel or missing gears. It's also important to note that you do not necessarily need to replace the torque converter because the fluid is burnt. The pan filter will generally protect it from debris. However, inspect the fluid in the converter during the overhaul and perform the other torque converter visual inspections. The torque converter should only be replaced if the fluid from the converter has friction material in it, large metallic particles, or the converter does not pass the visual and end play inspections.
If the fluid is pink or milky, the transmission must be overhauled since it's contaminated with engine coolant or water. Also, replace the torque converter since the coolant may have damaged the friction material on the pressure plate as well as damaging the friction material within the transmission itself. After inspecting the fluid, check the line pressure. If the pressure cannot be controlled by the pressure control solenoid, it can cause many different concerns, including shudder. If pressures are within the ranges indicated in the service information, then use the Tech 2 to operate the pressure control solenoid through its range of control. The pressure on the gauge should move with the command from the Tech 2. If the pressure is always excessive, there may be shift quality concerns. If the pressure is insufficient, the shifts will be soft or slipping and can produce a shudder. Both situations require checking the pressure control solenoid and the related hydraulic circuits.
With the preliminary information noted, it's time for a road test. The booklet for this GM Service Know-How release has a special road test for shudder diagnosis. However, realize that the road test in the service information will still work and is more thorough if the concern is more than shudder. Basically, the shudder road test has two phases: steady throttle operation without TCC operation and steady throttle operation with TCC operation. Here, you're basically trying to identify whether the condition is truly TCC shudder. Furthermore, here are two important tips.
Do not try to use slip speed information on the Tech 2 to observe shudder. The slip speed data typically cannot react rapidly enough to catch the high-frequency slip variation that occurs during a TCC shudder. The data will only show a static slip level. If testing doesn't provide conclusive evidence, get some more information from the customer and road test the vehicle with them if necessary. Let them do the driving to see what they're experiencing and when it occurs.
A good transmission technician should have a basic knowledge of engine operation and diagnosis. This knowledge can provide the evidence required to conclusively determine that the concern is in the engine, not the transmission. Although the actual diagnostic path will be determined by the fault, here's a review of what the drivability technician can typically look at.
As shown earlier, misfire counters are located in the engine data list on the Tech 2. These can be used to identify which cylinder is misfiring and can provide information even when a P0300 is not stored. The engine's air intake system generally has a system of ductwork with an air filter to prevent debris from entering the engine. Most newer vehicles will also have a mass airflow or MAF sensor located in the ductwork after the air filter. The MAF sensor shows airflow in grams per second. If the air intake is damaged or restricted, it can prevent sufficient airflow to the engine, reduce power, and potentially cause a misfire. Inconsistent fuel supply, something as simple as a clogged fuel filter, can also cause engine juggle, which can feel like TCC shudder. The system uses a pump to provide fuel to a fuel rail for the fuel injectors. Excess fuel is directed back to the tank by a pressure regulator. The injector test light, commonly referred to as a Noid light, can identify if the injectors are receiving the pulses for firing. Checking the fuel pressure can isolate any leaks that could be resulting in fuel starvation. It will also locate high pressure, which can result in excessive fuel delivery and misfire. The fuel injector coil test and balance test both require a special tool and a test harness for the specific vehicle. On newer vehicles, the balance test is a function of the PCM and a Tech 2. These tests check the operation of the injector coil and the basic amount of fuel delivered when the injector is energized. Injectors that do not operate electrically or mechanically can be isolated. Fuel trim and oxygen sensor readings can also be very useful. Trim numbers, either negative or positive, indicate that the PCM is trying to compensate for the operating conditions, running rich or lean. Generally, the pre-catalyst oxygen sensors will fluctuate between 300 and 600 millivolts, and the post-catalyst sensors will be much flatter. A malfunctioning sensor can very easily cause a misfire. However, there is generally a DTC with this condition. A basic test for the secondary ignition system uses the ST125 spark tester. It will provide a bright blue spark when the coil provides sufficient voltage. Some systems will require additional steps to use this tool, since they do not use spark plug wires. If the tester does not provide a bright blue spark, the plug will not fire, and there will be a misfire in that cylinder. Also note that a good spark doesn't indicate that the plug is being fired at the correct time. When equipped, make sure plug wires are not crossed and that the engine is being fired in the correct order. There is also the possibility there is a sensor fault that did not set a DTC. The throttle position or TP sensor is an example. The TP sensor swipes a potentiometer as the throttle blade moves in response to the driver's input. It is possible for a bad terminal in the potentiometer to cause a signal dropout. This can momentarily cause an abrupt fuel mixture change and resulting juggle. Regardless of the sensor, a technician can make sure it's providing a signal and that the signal is within the range indicated in the service information. If a mechanical fault is suspected, there are several tests that can be used to isolate it. The manifold vacuum test, the compression test, the cylinder leakage test, and the restricted exhaust test. When not operating correctly, emission systems can have a dramatic effect on the operation of the engine. The following are the primary emission systems: EGR, EVAP, secondary air injection system, PCV. For example, the EGR system is used to reduce emissions by allowing exhaust gases into the combustion chambers. Generally, the PCM compensates for the operation of the EGR. However, if it is malfunctioning, it can produce a juggle. A common concern with EGR is carbon deposits on the pintle valve, which allows exhaust gases into the intake. Since the PCM is not commanding the EGR operation, it does not compensate, and engine performance is affected.
There are two primary codes related to the TCC in most current vehicles. TCC shudder can be accompanied by one of these codes: P0741, TCC stuck off; P0742, TCC stuck on. Now the 4L60E also has a DTC P1870. There's a service know-how that thoroughly covers how to handle this DTC. If a DTC P0741 was stored, the PCM detected a high slip speed when the TCC was commanded on. Although this can be an internal torque converter malfunction, there are several other transmission components that are much more likely than a torque converter malfunction.
When inspecting components, maintain a clean working environment. Contaminants from the work area can result in misdiagnosis. Components that can contribute to a P0741 include the TCC solenoid. You'll need to look at the mechanical, hydraulic, as well as electrical operation. Regarding electrical, check the external connector as well as the individual internal connections. Also, check the harness. Look at the TCC valves. Are they stuck or damaged? Are any of the TCC hydraulic circuits blocked, restricted, or leaking? You'll need to check at the valve body, separator plate and orifices, and transmission case. On transaxles, check at the channel plate and drive gear assembly. On transmissions, include the oil pump. Check the turbine shaft on all models. If no damage is found, consider torque converter damage. However, take the time to thoroughly inspect the torque converter before replacing it. We're going to review torque converter inspection in a few moments.
If a DTC P0742 is stored, the malfunction is in the hydraulic or electrical systems. This code cannot be caused by a damaged torque converter.
If release pressure is available at the front of the TCC pressure plate, the TCC cannot stick on. GM has inspected many torque converters with this code and has not found a single converter where the pressure plate is stuck on the turbine splines in the TCC applied position. When inspecting for the root cause of a P0742 concern, look for things that would provide fluid pressure to the TCC apply circuits. This includes stuck TCC control valves, damaged solenoids, leaks between pressurized circuits and the TCC apply and release circuits, and the electrical system wiring for nicks or cuts.
If a TCC code is not stored, the malfunction may not be to the point yet where it sets a DTC. However, it can still cause a shudder. Make certain that the shudder has been isolated to the transmission before beginning inspections. The inspections that must be performed are very similar to those outlined in P0741 and P0742 diagnostics.
It's important not to overlook the effect of trans fluid on shudder. When degraded, it can lead to a shudder condition. Take the time to inspect the fluid in the pan. Look for debris and metallic particles. A small amount will be normal, but large chunks indicate a malfunction. Also, if a non-approved ATF was used, transmission or TCC shudder is likely. If the torque converter is suspected as the root cause, there are several inspections that can help confirm this. The first is an inspection of the fluid inside the converter. The fluid should be red or red-brown in color and should not have large chunks of debris. Some metal particles looking like glitter are considered normal. However, friction material or large chunks of metal indicate that the torque converter is damaged. If the fluid is burnt or dark brown, the converter must be visually inspected for any signs of damage. However, burnt fluid does not necessarily condemn a torque converter. If the converter is reused, drain as much burnt fluid from it as possible. The small amount left over won't affect the TCC operation once new fluid is installed. A thorough inspection of the torque converter is necessary during a transmission overhaul or when suspected as the source of shudder concern. All of the following conditions will require torque converter replacement. When inspecting the welds, look for porosity, cracks, and evidence of leaks. This is where installing the leak die can really pay off. Also, check the lugs for stripped threads, and then inspect for a broken or cracked flex plate. Next, inspect the hub bushing for damage including cracks, spalling, and gouges. Any of these will allow fluid pressure to push past the converter seal. This will create a leak and can prevent correct TCC operation. Next, check the outer hub surface. Look for wear damage and cracks. This damage can cause a leak and, if severe enough, can affect TCC operation. Also, check the converter pilot for damage. If the land at the end of the pilot is rubbed down, the converter may not be able to maintain the correct rotation axis. This can cause a vibration. Check the converter for bluing, the result of excessive heat. Check both the general torque converter and the area between the lugs on the cover. If a blue ring is found between the lugs, the TCC has been overheated. This can definitely cause a TCC concern, including shudder. Ballooning is where the torque converter has expanded as a result of excessive pressure in the converter. The end play check is the only way to determine if the converter is ballooned or if there is excessive wear of torque converter components.
Remember, the goal is to separate trans-shudder concerns from engine juggle or a shudder from the driveline or chassis. The following are tools that can assist in root cause diagnosis of trans-shudder concerns: electronic vibration analyzer, or EVA, chassis ears, rubber hose, Tech 2, and line pressure gauge and connectors.
The electronic vibration analyzer provides the information necessary to isolate vibrations to components. Although it is relatively easy to set up, interpreting the data requires some knowledge of vibration diagnosis. There are courses available on this topic. The chassis ears is a good tool for isolating the source of vibrations that cause noise. The tool has several vehicle sensors to provide audio feedback. Although a simple device, the rubber hose can be an excellent tool for transmission noise diagnosis. Connect it to the vent of the transmission. Then listen to determine if there is an abnormal noise. Make sure to compare it to the same transmission in a different vehicle for an indication of what is normal. The Tech 2 provides feedback on what the PCM sees and anything that it has detected. The last tool is the line pressure gauge. It is the only way to determine if the line pressure is within specification. If not, many different transmission concerns can occur.
As you've seen, accurate shudder diagnosis requires coordination between the transmission technician, the drivability technician, and the chassis technician. All too often, the torque converter ends up being the innocent victim, and a customer comeback is on the way. Now it's time to complete your look at torque converter issues by reading the accompanying reference booklet for this GM service know-how. Be sure to read it thoroughly. When you've completed your review of the materials, there's a test to certify your efforts on this training package. You'll find the test at the GM STC website on the World Wide Web. Until the next GM Service Know-How release, we wish you every success in fixing them right on time, the first time, every time.
All testing for the GM Service Know-How program is now accomplished through the GM Service Technical College website. The interactive voice response system is no longer active. To receive credit for this course, please access the GM Service Technical College website at www.gmstc.com and select Training Management from the menu. This will take you to the Training Management System. A valid username and password are required for this portion of the site. Once you have been granted access to the system, select the Tests option. From here, you will be presented a list of available tests. Select the test you wish to take and follow the prompts. This testing procedure provides immediate results at the completion of the test and is linked to the GM Service Technical College Training Management System. Your opinions and suggestions are welcome as a way to improve future GM Service Know-How releases. A survey form is available at the end of the course test.